Okay, now we're back. I wanted us to review a simple problem which encapsulates all the properties we've reviewed of integration. So here I propose that we find the integral of a vector. We don't care what this vector is, what it encodes, but let's call it vector q bar. And this vector depends on the variable x. It's a three-dimensional vector. The x component is 4tx squared, while the y component is 2x, and the z component is 1. Okay, so again, let's employ all the properties we know about integrals. Notice that our vector here is nothing more than a sum of three terms, or maybe let's say a difference, a sum. I think that's good enough. So we have three terms. We have this term, and that term. So we here have to employ one of the properties that the sum of the integral of the sum is nothing more than the sum of the integrals. So what we could do is we could distribute our integral operator. So this will effectively look something like this: 4t x squared dx I hat minus the integral of 2x j hat plus the integral of 1. I'm sorry, I'm missing a dx over here. Over here there should be a dx. Okay, we have a dx and then k hat. We now need to carry out the individual integrals of these three terms, or three components if you like. Okay, so let's start off with the first component, the I hat component. Notice again that the integral ought to be carried out with respect to the variable x. What that means is these two terms, as far as this integral is concerned, are nothing more than constants. So these terms can be moved out of the integral. This effectively means this is nothing more than an application of the second property we spoke of in the other video, that if you have a constant, you can move it out, or you could move it inside of the integral, depending on where it's useful for your case. So let's do that over here. So we would simply pull out the 4 times t, and then we'd be left with the integral of x squared dx, and this would constitute the x component, or the I hat component. The same could be done here. 2 serves the same role that 4t played in this I hat component. So we could move the number here, the constant 2, out of the integral, which then would look something like this. Minus 2, then we're left with the integral of x dx, and this is the j hat component. Plus, notice in the final term here, the final component, we don't have the x variable present, but actually there's a nice way of introducing this variable without changing the expression. That is, we could write x to the power 0. Here, therefore, we can rewrite this as the integral of x to the power 0 dx in the k hat direction. Now we have something to integrate. Of course, here for mathematical consistency, we will say that x should never be 0, otherwise it introduces other issues. Okay, and what's left here is nothing more than the application of the polynomial integration recipe. The case here, we have x to the power 2, that is, n is equal to 2. Over here, n is equal to 1, and over here, n is equal to 0. So then we go ahead and employ this. This would look like 4t, and we again, remember, would increase our exponent by 1, which would simplify to 3, and divide by the new exponent. Well, the new exponent is 3. Because of generality, we have to include a constant. I will choose my constant to be c, and because I'm anticipating that there will be a constant from this term in the j hat direction and in the k hat direction, I will call my c, I will label it with Ci, signifying that this Ci issued from the ith component. Okay, let's go on to the second component. This would be 2 times x to the power. Here we have to increase our power by 1. Initially it was 1. Now we have to increase it by 1 and then divide by the new exponent. So doing so leaves us with something that looks like this. And then, as I've said, that because of generality we have to introduce a constant. And again, our constant here I will signify with Cj. Maybe I shouldn't put a het, otherwise it would confuse. So this is just simply C sub j, and this makes up our jth component. We carry out the same procedure for the final term. We're going to end up with x plus C sub k, and this term will constitute our kth component. This, therefore, is how you would carry out an integral of a vector whose components are functions of a variable x. This type of integral is an indefinite integral because there are no limits supplied. In class we did discuss the case where we have limits, and unless you guys have questions on that, I will not delve into that. In the next video, I would like to talk about a physics problem where we demonstrate how to use this. Okay, see you in the next video.